Before we start the first session, just let me say a few words personally. It is true that when we organize a conference through internet, we lose personal contact. This is a new idea, which personally I don't like, because we lose the contact between ourselves. When we are in a conference room, we can always discuss, we can always say a few words, each one of us. We can always talk to each other. So this is the isolation which I discussed before. Now, before I continue, let me remind you to you that there are no questions after lectures. All questions should be written downstairs on the Q&A of the Zoom screen, and then we will read and discuss them during the Q&A session. It is important for all the speakers to be very careful with time, so that if it's 20 minutes, it is 20 minutes, not 30, not 40. As usually, in all conferences, there are last moment changes, so which I will announce to you later. For example, in session 1, the first lecturer is Professor Skoulos, then we will have Professor Amvoutis, and then we will have Professor Mouzakis. Since Professor Amvoutis has a very important professional appointment. Then at the end of the session, we have a new presentation by Mr. Panagiotis Stefanidis. So at 12:50, we have one more presentation of 20 minutes by Mr. Panagiotis Stefanidis. I think we can start slowly. The first speaker for today is my very good friend and colleague at the same department, Professor Michael Skoulos, Michalis Skoulos, which I am very glad to see him here. I have to point out that Michael, has devoted all his life and research to the quality of water all over the globe. He has worked very hard in the Department of Chemistry to establish a laboratory of environmental technology, correct, Michalis?
Yes.
And he travels all over the world to promote sustainable development and anything else that has to do with the quality of water. It is a great honor for us to have Michalis with us. And Professor Michael Skoulos is going to give us a speech setting the framework and message of the conference works. Sustainable development in a healthy, human and capacitated world. Professor Skoulos, please go on.
Good morning. Good morning, Andonis. Good morning, our chair. Good morning, dear colleagues. It is a great pleasure and honor for me to be here. And as the chairman said, I would like to contribute here, setting the framework for all different sessions, and allow me add to what he said, that here I also represent the UNESCO community as chairman, as a director of the UNESCO chair at the University of Athens on sustainable development, management, and education. And I would like to repeat a little bit some of the things said already, that this very first Athens Calls Athens conference, a very important initiative, under the theme Man and His Creations, offers an extremely important, a formidable opportunity to all of us, people of different countries, of different backgrounds and disciplines, who are still inspired by the eternal principles and ideas originating here in Athens, ideas that are still vivid and valid today, to exchange our views and also suggest appropriate methods and approaches addressing the current and the very many emerging challenges of our planet and our society. Most of these challenges are linked to man and his creations, is what actually is the anthroposphere. Anthroposphere includes man and his creations over the natural environment. So these pressures created by man and his creations, by man himself, overpopulation, but also his mentality that pushes him to more and more unsustainable consumption and production. Erratic economies, ignoring the natural capital, ignorance, lack of education, inefficient mechanisms in management and administration are all interlinked in an ever-increasing complex world. And allow me to introduce a little bit this evolution. We started with man, few hundred, if you wish, few tenths or 100 even, 1,000 years ago, as an integral part of nature. So at that time, theoretically, there was no environment of the man. Man was part of it. Environment became from the moment that human being understood himself, herself, as something different from all the others. So this first move created little by little the environment. From the moment he started using very primitive tools, he started creating the technological, the man-made environment. At the same time, he started communicating with people. He started painting, or he started language, and later on, all different aspects of culture. So a second part of the environment is a cultural environment and social. And at the same time, he started asking himself, what is my connection with the universe? Who I'm from where I come and where I go. So the spiritual environment was started. So we have three aspects of the man-made environment. What is around man is partly made by man and partly perceived by man. So little by little, these, while the natural environment remains the same, the other three aspects, technological environment, which is today more or less we call it technosphere, the cultural man-made and spiritual, not evenly developed, they have created this anthropogenic environment. This anthropogenic environment is what we call anthroposphere. And for us natural scientists, we always have to see the relationships and the ratio between the anthroposphere and the natural spheres, the geosphere, the hydrosphere, the atmosphere, and the biosphere. Of course, man is part of the biosphere, but there's a special relationship there. So what is in front of us is actually something new. It is something new in the sense that the natural resources remain exactly the same. We have the same photosynthesis, we have the same water, we have the same soil, the same and even less biosphere, but all the rest is gigantic. I remind you, since we are entering the year of the Greek Revolution of 1821, that all the ancient civilizations, including the Greek one we celebrate in a way today, were done when the human population were few tens or hundreds of millions. And the first billion coincided approximately with the Greek Revolution. And from 1821 to the destruction to the 1922, we added the second. And from 22 to 60, the third. And from 60 today, we reached almost 8 billion. We understand that there is no species that has this kind of evolution. And this is something that many times we don't discuss for political, religious, and other reasons. So the thematics, as introduced already by the chair, by Professor Kalokerinos, all 6 technology, society, health, environment, economy, and humanities already indicate 2 things. First, that the themes need somehow to be approached in a modern way. In a multidisciplinary, but most importantly, in an intra or transdisciplinary way. A very difficult thing, because you need to have a minimum of knowledge of the other sectors, and particularly the way what we try to teach at the University of Athens. Actually, after my interventions here, after this session, I have to go for postgraduate course at the university, and this is one of the things I have to insist, is the transdisciplinarity, how to put the right questions, to know what kind of questions I can put and what I can expect from the other disciplines. So also this is important for our conference today. But already the themes show the philosophy, design, and overall methodological approaches that are followed and are going to be followed for the works of the conference. In fact, we are talking about using all these in approaching sustainability. And to be more precise, to approach sustainable development, which is a monodrome today, is the only way that we can proceed, because this is the only type of development we have as a tool in front of us. Let me also insist a little bit on the on how we see that the works of the conference could proceed. First of all, of course, we need to approach approach our goal in an efficient and effective way. To reach a safer and healthier world. This is the contribution we can do. The second is, of course, some new results may come, some interesting results may come out of our deliberations. But also through our works, we hope to help in orienting and framing this new creature, Athens calls Athens, showing the directions for the next steps. Hopefully, we view this with optimism, and I'm sure that more will join, understanding better our direction. Let me say that many of the words of the themes are directly linked with sustainable development. In 1992, sustainable development was presented a little bit like a Greek temple with three pillars: environment, economy, and society. The question is always, for what, for whom, and how? Of course, it is very difficult in so few minutes to get in details, but I try my best in understanding, first of all, what is the what and for whom. The what and for whom is for a better, humane world. That means a society physically and mentally healthy and secure, safe. Safety and security, particularly now with COVID, we understand even better, that is an important thing. It's an important thing, the peace, not only for as an absence of war, but also a peace in our mind and in our society. In this sense, safety goes far beyond national security and independence. It includes conditions safeguarding human rights, peace, as I said before, decent living for all people and all citizens. So, for example, my dear friend Andonis mentioned my work on water. One of the things we have promoted all these years is the so-called nexus, the safety of nexus, which is not only water, is water, energy, food, ecosystems, because all these are interrelated. And today, there is no safety for a country without the safety of this nexus. And the how is where we as universities play a role, is through capacitated work. That means an empowered, equitable and responsible society, including the most vulnerable parts of it. Don't forget that 1/4 of our population today lives in extreme poverty with no access to water, safe water, and sanitation. You understand how vulnerable not only these people, but the entire society is because of that. So the above encapsulate key ideas of the Athens Calls Athens initiative, with key tools, as I said, awareness and education, cooperation on cultural, socioeconomic, scientific issues, and all these are linked with the so-called UN Sustainable Development Goals. These have become the key direction for all countries, is an achievement of humanity, because all countries unanimously have accepted, after many, many years of negotiations, these 17 goals and 169 sub-goals, targets, that encapsulate all necessary steps and targets for our future. I don't have the time to get into that. Number 4 is education, and number 4.7 is for education for sustainable development. To better understand visualizing sustainable development and how we do that through governance. So the foundation is governance. And as a chemist, I have changed the previous visualization, having the tetrahedron as the most stable structure, as we know. And this also brings the most important message here. It has been accepted universally as a good visualization. Why? Because sustainable development needs to bring together environment, society, economy. We are talking about socioeconomic, environment, economic. So within the tetrahedron, there are different points closer to environment or closer to economy or society, depending on each country and even each region. And it's an evolving principle, but it has to be there, encapsulated there. And who is going and how this is going to be managed and brought together? Through governance. So governance has several tools. It has as tools institutions, of course, regulation, administration, institutions in general, science and technology, where many of us work, and education, awareness, and culture, appropriate culture. All these are parts of the conference. So this is the analysis of governance. Governance requires, again, a mixture of institutions, of science and technology, through which we enhance, increase the carrying capacity of the systems, and education, awareness, and appropriate culture for the understanding of where we go and how we should go there. In fact, insisting a little bit on the last thing, because Athens insists to a certain extent on culture and on changes. We have to understand what changes mean. Changes mean, on the one hand, perhaps total reconstruction and total changes. But on the other hand, at the same time, we may go back to some of the things we have neglected or we have misunderstood. So it is a pendulum where the entire spectrum is culture. Conservation of our roots and going back for inspiration to the roots is equally important to total construction of new things. And in between, we have complementation, reconsideration, adaptation. And this all is linked with science, technology, education. It's very important to understand that. And I think that culture is a unifying, in this wider perspective, is a unifying cement among all the themes, and is a very important aspect of the Athens calls Athens approach. The culture for the third millennium is actually needs this combination of very advanced science, but also approaches rooted on eternal values and principles: democracy, human integrity, evidence-based decisions, reason, freedom of speech, seek of virtue that has been forgotten, and of course, privilege of the public good versus interests of individuals, as Pericles in this very city said. So most of these things were developed in this very city. And I think that with these comments, I will stop here and thank you for your attention.
Thank you very much, Professor Skoulas. I hope you will be able to be with us at 1 o'clock with the Q&A session. There are some very nice questions which we have for you. Your lecture was very philosophical, and I would like to thank you for keeping the time very precisely. Now, in 5 minutes exactly, we are going to have the lecture of Professor Amoulitis. So just give me 5 minutes exactly to continue with Professor Amditis. Ladies and gentlemen, the next presentation for today is Professor Amditis, and Professor Mouzakis will be the next speaker. Professor Amditis will give a presentation with the title Understanding the Internet, Digital Age or New Technologies, and Environment or New Means of Transportation, Science and Tech Achievements. Professor Amditis, please go on.
Thank you, Mr. Chairman. Thank you for the introduction, and thank you for inviting me here in your conference. I hope you can hear me well. So I will try to share my screen. Okay, I hope everything is visible to all of you. What I'm going to try to speak to you here is about smart mobility, what we call smart mobility, especially in the framework, in this new era of digitalized environment that we are living, in the framework of the fourth industrial revolution, and of what we call smart societies, not of tomorrow, I would say, but of today, since this type of smart societies are already here in our hands. So, as Mr. Chairman mentioned, I'm a research professor at ICCS, Institute of Communication and Computer Systems in NTUA, National Technical University of Athens in Greece. And I'm also chairing the Intelligent Transportation Systems Society, a European organization which brings together all stakeholders in the area of mobility. So I mentioned before the fourth revolution. In the first industrial revolution, we used water and steam power to mechanize production. The second one used electric power to create mass production, while the third one used electronics and information technology in order to maximize production. Now, a fourth industrial revolution is building on this third one, the digital revolution, as we call it, that has been occurring since the middle of the last century. It is characterized by a fusion of technologies that is blurring in reality the lines between the physical, digital, and biological spheres. The technological change and the new technologies have been and will be in the future one of the main driving forces in the development of societies. As indicated by the history of our globe, the economic development of the world has its milestones which pace up, slow down, or stabilize its speed. The use of the power of steam in the mechanization of waving plants, the development of iron production, with the use of carbon gave grounds for the first industrial revolution at the end of the 18th century. The second industrial revolution, dated at the turn of 19th and 20th centuries, is under a serial production of machines, development of motorization, the radio, the telephone, and a new division of labor. We date the third industrial revolution after the year 1970, and it's connected with the use of electronics and IT in the automation of production, with the application of new solutions to the organization of production and new communication technologies. The fourth industrial revolution is practically at the beginning of its development. It's quite interesting to note here that although the previous revolutions had more or less 1 century between one to the other, the fourth industrial revolution occurred just 50 years after the introduction of the third. So we have a speed up of all these changes all over the world and in all areas. So what is also relates to this fourth industrial revolution is what we call this cyber-physical world. I mentioned before this blurring of limits between the cyber world, the physical, and even the biological world, and this is reality. More and more today, all these are connected in a way that it cannot be separated from each other. We have technology innovation, we have data revolution. As many economists say, data are the new petroleum of the economy, so they're going to play the same role in the new era as petroleum and fuels, carbon fuels played in the last one. Automation is in the middle of this discussion. Smart systems, integrated and distributed. We go towards more and more on-demand services, and mobility is an example for that. I'm going to discuss about it. But more important is this explosion of disruptive technologies, which is really changing the way we are doing things, the way we are connecting with each other, and the way we are offering services in our world in all fields. As I mentioned, I'm going to focus on the mobility in this new digitalized era. And here I have some keywords that you can see what is really that characterizes mobility today and tomorrow. So smart, connected, automated, digital as all aspects of our world, multimodal, so correlation of all means of transport together, user-centric, green, and electromobility is one of the aspects that we are discussing more and more today. Integrated, because we need to offer integrated services to our citizens, and on-demand services in order to avoid loss of resources and too big expenditures about providing these services, but also reducing the carbon footages of mobility. It's going to be shared, so not going a little bit far away from the classical model of owning our own vehicles, but now going more to sharing vehicles, sustainable, and of course safe, which is one of the most important aspects. So when we discuss about smart mobility, in reality, we discussed about a well of tools, systems, and concepts, focusing on a number of different ideas and concepts on accelerating automation and connectivity for safer and smarter mobility, on reducing the environmental impact, delivering seamless mobility for all, including, of course, the need for advanced traffic management, multimodality, and all of them both for people and for goods. So logistics is also an important area in this discussion. Let's look a little bit on these items in more detail. So speaking about smart societies, until now, most of the people discuss about smart cities. I would like to a little bit go a level higher than that. So in reality, we speak about smart societies, where smart cities, of course, is an important pillar. And what we mean by smart society, we mean a concept where we successfully harness the potential of digital technology and connected devices and the use of digital networks in order to improve people's lives. And here in this slide, you see all the different aspects, all the different pillars of a smart society, from telecom to mobility, for climate to smart buildings and smart infrastructure, from governance to energy, and all the different aspects that are important for our daily life. And as I mentioned, here in this discussion, this presentation, I'm focusing on smart mobility. You can see below the data, as I mentioned, it's a horizontal aspect. It goes through all our activities, all our discussions. And of course, it is one of the most important items, and that is why we're doing all this discussion about open data, about transparent access to data, all these important things that we are discussing also in our country. What about urban mobility and mobility as a service? So how can we handle mobility of our people inside our cities, and not only our people, but also our goods? So one of the most important things in mobility today is how we can make the best use of our resources. and how can we be able to deliver seamless mobility for all. Again, we are speaking both for people and for goods, because both of them are important inside our cities and both of them have their effect on our daily life. So we are progressing towards a mobility management, an integrated mobility management, which is based mainly on automation, on connectivity, on green mobility, and on multimodality. By multimodality, we mean the use of all available means of transportation, both public and private, in an historical way, so we can offer seamless services to our citizens. So cooperation of the public and private sector in respecting the priorities for green, safe, and accessible mobility. One of the main aspects and main new concepts here is what we call mobility as a service. Some people is calling that also DaaS, delivery as a service, because it contains also transportation of goods. It's this idea of integrating all various forms of transport services into a single mobility service accessible on demand. So that means that we have access to all means of transportation, both public and private. We are having the possibility to have a single journey planning through platforms, through mass platforms, and also very important ticketing options for the user. This means in reality that we want to go from point A to point B. We don't care what type of means we're going to use. We don't care about how to pay. We just plan our trip. The system is providing to us all available options, giving us the opportunity to use these options and also allow us to pay in one single point for all the means that we're going to use. So this, you understand how they're going to change the way of our mobility, the way of moving inside our cities, but not only. And the whole idea is at the end of the day to provide reliable and advanced mobility capabilities, mobility services, including all the information that we need during our trip. Another important aspect is integration. And integration becomes more and more important in our lives. We speak about integration of transport modes, integration of different concepts of today, including what I mentioned before about mass, but also connected automation, green mobility, and all the different aspects that we are discussing, we are using, and we are going to use in the near future. Together with all these disruptive technologies like artificial intelligence, Internet of Things, the new mobility environment that is going to come to us very soon with 5G, blockchain, and many other similar activities towards a fully integrated and digitalized transport system, again, for moving people and goods everywhere and in every condition. So this integrated transport system is going to bring together all the different aspects which are isolated today. So moving from independent elements to an independent ecosystem, combining all currently independent transport elements like electric vehicles, automated vehicles, public transport systems, road infrastructure, all the different elements, and the cooperation with other sectors like the energy sector, fleet services will bring, and all of them together will bring convenient, safe, and economic mobility with, and this is very important also, with less impact to our health and the environment, building what we call the smart societies of tomorrow. I recently, a few years ago, introduced the term the Internet of Mobility in order exactly to describe this new integrated transport idea, this integrated transport system. So we're speaking about an innovative, holistic mobility concept where all the different elements that I mentioned before are capable of operating together in a cooperated and integrated way, addressing in real time the needs of all and each separately passenger, participant to the mobility scheme, applying different levels of automation and supporting all transport modes for both people and goods. And why I called it Internet of Mobility? Because this, in reality, it gives scheme very similar to Internet of Things. If you see all these different elements as modes of the same network, then of course this can create an idea of an Internet of Mobility. And this is a term that I found it is very easy to understand, both for people, for users, but also for public authorities and experts. Let's discuss also a little bit on connectivity and automation. These are forms, things that are quite well understandable also by our citizens, by people, and they have their own interest. So first of all, automation, we are we are hearing, we are reading on different news, all the different announcements about automation. This is something that we are well aware also from movies and from books, but it's something that is here, so automated vehicles. And what we mean by automated driving is this capability of using our vehicles without the intervention of ourselves, of the driver. So the capability of moving by, of allowing the vehicle to drive by itself, different levels of automation, of course, using its own sensors and its own capabilities. Why we want that? Because automated driving will improve road safety and address inefficiency in traffic flow while mitigating the environmental impact of road traffic. We need to remember here that according to all studies all over the world, 90% of all accidents are related with human factors and with errors of drivers. So this type of systems, this type of solutions will in a way support us in reducing this huge impact in safety and in accidents. All these things will be connected in vehicular networks, the Internet of Mobility I mentioned before, together with the support of advanced traffic management will provide us an ecosystem of connected and automated vehicles, a convergence of the different modes and systems that will allow us really to go to the next level of smart mobility that I mentioned before. This is just to give you an idea how automation and all the other mobility aspects are connected with information services, with data in reality, and to see how, as we are advancing both in the capabilities of automation but also in the IT capabilities, we are going into more advanced services and more advanced functions and capabilities. All these things will create an even more complex environment, especially the transition period where we're going to have a mixed traffic environment, both automated but also classical vehicles will be traveling in our roads. And this is why traffic management, mobility management will play more and more an important role in our traffic management, in our mobility systems. A few words also about logistics. Transport is also one of the most important aspects, most important pillars for the logistics chain. We have seen in the recent pandemic crisis the importance of logistics, the importance of providing goods on the right moment, in the right place, and transportation is one of the most important elements. And this is why we expect that this smart mobility revolution will bring also a revolution on the logistic sector. I spoke about data before, and data will be really the key asset for all these aspects, not only for mobility, of course, but also here in this sector. This will be the key, the most important asset for the future mobility. And this is why we need really proper data management, access, and also availability for all players, for all stakeholders in the area. This is something that both our government, but also all the member states and the European Commission is really putting a lot of focus and attention. So we are living in an era of challenges and risks. And one question I am hearing in many panels I'm participating is the new mobility I described part of the answer. And if we take a look very fast in some of the challenges we are looking today, for example, COVID, the pandemic, this unbelievable situation we are living the last few months. Of course, smart mobility can play a major role here and support how we can really address this huge problem, as this smart mobility concept really provides on-demand services, catering then for social distancing while complementing all the public transports. What about recession? This whole idea will bring new investment opportunities and new markets. So both the Commission and the Member States and the governments believe that investing in smart mobility will create new opportunities for development and new opportunities for new markets. The same is true for the huge challenge of the climate change that we are looking at. The Commission has already announced the Green Deal, which is this idea of making Europe a climate neutral continent by 2050, and smart mobility, exactly because of issues like automation, like electromobility, will play a major role also there. And I would like to close my presentation with this last slide, some ideas, some expectations, what we are expecting by 2030. So we're expecting to see more and more automated vehicles on our roads. Eco-friendly vehicles, eco-friendly mobility will gain more and more a significant market share. We have seen also in our country how electromobility becomes more and more important, and new investments are also there. We will see new types of vehicle integration, also new ideas, for example, drones, evolution of scooters, mainly electrified, and all of them integrated in concepts like MaaS, which I described before. This will lead to a decrease of vehicle ownership. We are going more and more in buying mobility services and not vehicles, so we're speaking about collective transport. And we're going to see more and more an evolution on infrastructure, more and more physical and digital infrastructure will be totally connected to each other. We're going also to see a long transition period of mixed traffic, where all different concepts, vehicles, like I described, will be together, and this will be a great challenge. And we're going to see continuous changes upon green transport priorities, as this will become more and more a norm and a very important issue for all our countries and all our citizens. Thank you very much, Mr. Chairman. I hope I didn't spend too much time.
Thank you very much, Dr. Ambritis, for the excellent lecture. I realize that we are in the middle of the fourth revolution.
Indeed.
Which we don't know what will happen in the future. Everything is very good. But sometimes I think that we are too small for what is happening around us. Unfortunately, Dr. Ambritis will not be able to be with us during the Q&A session. Is this correct?
I will try my best. I have an important meeting to attend, but if it finishes before 1 or at 1, I will try to join. In any other occasion, I will be able to answer any questions offline, of course.
Okay, that will be excellent. If you can close down your share screen, so that we can go to the next presentation by my good friend, Dr. Mouzakis. Professor Dionysios Mouzakis is a very good friend of mine. And he is going to give us a presentation with the title Additive Manufacturing Technologies, the Unforeseen Revolution of the 21st Century. Dennis, please go on.
Thank you, Professor. Thank you very much. I would like to welcome everyone and thank the organizing committee on this invitation for me, which is very important. And I'm also very, very sorry that due to the COVID pandemic, this hasn't grown to cover the whole planet cities called Athens. So maybe next year we will have another chance, Professor, to enjoy our colleagues' company. Without saying anything else, I would like to share my screen now with you. So let's say, please let me know if everything is okay. And Yes, I will begin by thanking Professor Avditis because he made a very nice introduction into the fourth industrial revolution, and which is a part of my presentation actually. Now, I come from the Hellenic Army Academy, as it is known, the Στρατιωτική Σχολή Ευελπίδων, or the School of Aspiring Young Cadets, as it is known for the last 190 years in this country. And I have to say that a common misconception is that we are not, but we are actually the oldest academic institution of the newly founded Hellenic state in 1828. So it was first based in Nafplion, founded by the first governor of Greece, and the first organizer was a Bavarian officer called the Count von Heidegg, and the first commander was Italian called Saltelli. And we are actually in a beautiful campus based in the southern of Attica. We have about 1,000 cadets in 4 years, and from the next year, it is going to grow very, very much to 1,600 cadets. We are now 40 faculty members, and we have also 30 teaching assistants. You can see some pictures of our huge campus down there, but let's go on to the importance of the presentation. This is the outline of the presentation. We are going to give a small introduction into the industrial revolutions already given, the history of additive manufacturing technologies, some main technologies, some applications, of course, the important economical facts. Economy drives our civilization, as it seems nowadays, and we will finish with conclusions. Now, I will repeat the same. The first industrial revolution was the mechanization of industry by the use of mass production, steel, and steam. And the first steam engines, of course, were used to mechanize this production, and all went well. And we went into the second industrial revolution. We started in the early 20th century with the famous Ford production line, and also his famous remark that anyone can have a car as long as it's painted black, because black was the paint that dried most in the shortest time, so they could produce more cars for the consumers very, very quickly. And this was, of course, the drive, unfortunately, the second industrial revolution for 2 wars that shocked humanity, the First and Second World War, which were industrial wars, so to say. And after all that, peace, of course, prevailed. And we went into the huge explosion of computers, the electronic revolution, the third industrial revolution in the 60s. And we have a very nice quote then from Popular Mechanics. Some guy predicted that computers in the future will be less than 1.5 tons in weight. And I think we have achieved that. And if you carry your mobile phone in your hand, and most of us cannot imagine the computing power or the feasibilities of this beautiful instrument that we carry along, or the sensing capabilities. And I make many, many jokes to my cadets as I teach. Many times I ask them to measure the constant of gravity using their mobile phones, and some of them like to throw their mobile phones on the floor and time the time it needed to reach the floor. So instead of using the accelerometer sensor application of their mobile phones. But yes, we have managed to miniaturize our mobile phones, and now is the time for the quantum revolution, which is the quantum computing age just starting, and many, many wonderful things are anticipated to come for the humankind. On this graphic, I just want to point out that revolutions used to happen. The first one took us about 1,800 years from the first steel making by a blacksmith, and until Henri Bessemer gave us his famous patent for the mass production of steel. And then it took, let's say, 100 more years for the second industrial revolution. And then it took only about 50, 60 years for the third industrial revolution, including the atomic age. in less than, say, 30 years, we went into the fourth industrial revolution, the cyber physical system, and was beautifully stated by the presentation of Professor Amvitis. I'm sorry. Sorry about that. Yes, we are now into the doorstep of the quantum revolution. For the first time in mankind is driving two parallel revolutions, may I say. We are driving the quantum revolution and we are driving the fourth industrial revolution. Can they be combined? Maybe. Maybe one can say that quantum computing, quantum electronics are a part of the fourth industrial revolution, or maybe not. The historics of the future are going to determine this. But let's go back to manufacturing, since I'm also a mechanical engineer and this is my field, so to say. So mankind, from its early industrial efforts, tried to make things in some ways. And these things were made either by hammering stuff, so by removing, let's say, excess material to fix, and this is subtractive manufacturing. Afterwards, it succeeded in melting metals from, say, some types of stones or ore, and it went into casting technologies and molding technologies, and this has accompanied us. But now a new beginning has come, and one can say, well, this is not so new, but it's a part of ancient technologies being put to modern stuff, to additive manufacturing. Up to now, our most modern, of course, drive in manufacturing was the computer navigated and controlled machines, which could even make material and remove material by even in 7 degrees of freedom, working so in 7 axes, so to say. And these were most evolved, and a very nice machine of, you can see the picture, could cost some millions in that case. But from the 60s, a new era began. No one could see it coming. Very few people were dealing with such techniques. And here in this slide, you can see the huge technology family of what we call additive manufacturing. I'm not going to read them all out. They are categorized in terms of how and what type of energy is being used to sinter or even solidify materials which are in the forms of powders, or in the forms of liquids, or in the forms of wires, or in the forms of ropes, and so on and so on. But it is already a huge family of techniques, which many of them are of industrial grade, so to say, nowadays. And just to give you a small historical background, back in the 60s, DuPont, which had already given us photopolymerized polymer resins, some people tried of DuPont to employ a laser and make a solid object out of a liquid resin by photopolymerization. And in Denmark, also, some guy called Svensson tried the same technique with a dual laser beam and even filed a patent. And from 1967 to 1984, this technique, polymerization, was being developed, but no concrete device to produce things was offered to the market. So they were all lab prototypes. In the early 70s, a company called Formigraphic applied the dual laser intersection and made the first commercially available laser prototyping machines. And all this caught, of course, the attention of the military and the aerospace experts. So DARPA went into funding these techniques, and this funding drove into better applications of the additive manufacturing technologies. But I told you back, it's not just a modern idea. Some guy, French guy, Francois Villem, in the 1800s, proposed that even making the ancient Greek temples was a kind of additive manufacturing, because they did not made huge pillars out of one stone like the ancient Egyptians did and all the other ancient people did, but they liked to make like a pyramid, let's say, out of spondylus, out of smaller blocks, construct huge temples. And this is actually additive manufacturing, or the way a sculptor make his clay prototypes or his clay molds by adding small pieces of clay and produces a mold to cast a statue, and so on and so on. So it's really an older idea. Back in the pioneers, in the 1980s, in Nagoya, in Japan, Hideo Kodama made a photo hardening procedure, and using UV now light for photopolymerization. In 1984, Alain Meotet, Olivier De Witt, and Jean-Claude filed a patent for stereolithography, and French company Alcatel, which they contacted, said this technique has no future. It has lack of business perspective. Now it's a laughing statement, so to say. And in the end of the 80s and start of the 90s, the explosion came in a company called Stratasys by a pioneer called Scott Crump, which marketed the first fuel deposition machine. And then on and on, we had the Z Corporation in Germany, and in Solingen Technologies. Also, MIT people worked very, very hard on this. And we had the first commercial engines to produce 3D printing. But it was the huge revolution with microelectronics and microelectronic technologies being very, very, very cheap, like Arduino microprocessors, which drove the huge explosion of the 3D printing machines available for hobby and home. Mr. Chairman, how long time do I have? Is it 7 minutes, I think?
I think you still have 9 minutes.
Thank you very much, Mr. Chairman. So how does it work? Usually, you build a 3D, a computer-aided design in your computer as per all the usual design technologies we use and software available to every engineer or every designer nowadays. Every industrial designer has a CAD program installed in his computer. So most of these programs can store the object into a three-dimensional stereolithography binary type of file, which can be then fed into another specialized software called the slicer, which actually slices the 3D dimensional prototype into thin horizontal or vertical slices, as shown in the graphic, which is also then translated into the language of the CNC machines, and this language is called G-code. After this code has been generated, it can then be fed into any 3D printing or additive manufacturing, industrial or hobby equipment, and a model is being produced or a product is being produced. So this is these are the four main steps of the 3D printing or additive manufacturing. Of course, finishing of the part may be required in the end. Now, some main technologies is the selective laser sintering, diffuse deposition modeling, stereolithography, digital light processing, and direct laser metal sintering. I will not bother you to present them in detail, just to tell you that the selective laser sintering uses a powder bed and the directed laser to solidify layer by layer objects. In the fused deposition modeling, we are using a specially prepared, usually polymer or enhanced polymer cord to feed it through a special micro extruder, which melts it and deposits it in the forms of layers like a loom, so to say, in a 3D object meaning. And you can see the example. This is very popular in hobbyist technologies. The stereolithography uses UV light to harden photosensitive resins inside a polymerization vat filled with resin. Similar is a digital light processing procedure, which focuses also a light source inside a polymer resin vat. And I will close with a direct laser metal sintering procedure, which uses a laser beam, a high energy laser beam, to solidify now metal powders or metal alloy powders or even super alloy powders in three-dimensional metal objects. And here on the center of the slide top, you can see an erratic design of a hinge by modern CNC technologies would be in a solid form. You can see how it was optimized for weight and still remaining, keeping its strength characteristics, but this design could only be produced by 3D printing by the DLMS technique. Now, can it change the world? Is it a revolutionary thing, so to say? Yes, it is the answer. It can produce things of many applications, even in the biotechnology, the implant area. It is also used to prepare things, stuff in the food industries, and we are going to see lots of, so to say, Star Trek prepared meals by 3D printers in the future. And of course, aerospace and defense are very much into it. We have already engines that fly, like the LEAP fuel nozzles engine, which is a 14-part, very important fuel injector. It can be produced by 3D printing in one part now, saving cost and fuel. So already mankind is enjoying these technologies. Some more applications, I will not stick with them very much. We have already ultra tough plastics to print out small planes, small drones, small UAVs, as shown here by Stratasys, or the US Army drone group of Perdix, which group themselves like a flock of birds in the air for several purposes, so to say, perplex the enemy radar. Some more applications, a beautiful vertically landing and taking off drone by Stratasys and Boeing collaboration. And some more applications in the future. Even the US Army had a container in Afghanistan equipped with 3D printers, obtaining designs by satellite to print some parts for their machines. Other projects, I will not stay with them, some ammunition being printed out, or even a handgun, or a buoy for the Navy. You can see the size of the printed material. Nowadays, we have patents for buildings, for 3D buildings already been filed. And some efforts of my lab, we have succeeded in printing out a small UAV in a hobby 3D printer. We have printed out a small vehicle, a six-wheeler. We have printed out artificial stones containing sensors for intruder detection. And to close with economic facts for additive manufacturing, it is very important because it is foreseen by 2030, 400 billion of the global economy will refer to these technologies. And it is very important. We will have 38.25% increase in the global annual income by 2021. And all sectors will be affected by this revolution. Some more economics, I don't think it's important. Anyone can read it. I would like to bother you with the stuff. They are analytical here. I hope all presentations will be made available to all participants. But I want to persuade you that yes, it is a very important revolution for all aspects of the human industry. And with the conclusions, I have to say that it is an indirectly green technology because It doesn't require making of molds, effort, energy, materials to make molds to produce stuff. It produces minimal scrap. So indirectly, it is a very green technology. Directly, is very energy efficient. It targets energy only in the area where the material is being fused together, where the particles or the liquid is being solidified. So in all together, excuse me, additive manufacturing is a very green technology. It's very cheap, it's very economic, but a handicap is it does not produce up to now terminal things, consumer products in the final consuming phase to be for the supermarket available and for the shelves. It requires some final steps to make finished products. So this is a small handicap. And of course, we cannot use all types of materials. We can even print in ceramics nowadays, but not all ceramics, not all metals, and not all plastics. Many, but not all. We hope in the near future this will be made feasible. If you like to read, there is a chapter there in an open book, totally free to download it and do some more reading. And I would like to thank again you and the organizers for this beautiful chance to give you this lecture.
Thank you very much, Professor Bouzakis. If you can close down your screen share.
Yes.
I have to point out that in chemistry, we are using 3D printing for making chemical reactions, small cells into which we make chemical reactions. Anyway, I would be very glad if you would be able to stay with us during the Q&A session so that we can ask some questions. Thank you very much.
Thank you.
Our next speaker comes from the same university, the Hellenic Army Academy, Professor Melagraki, who is going to give us a lecture with the title Cheminformatics Applications in Drug Discovery, Material Science and the Environment Underpinned by Artificial Intelligence and Machine Learning Methods. Professor Melagraki, please go on.
Yes, thank you so much for the kind introduction. Hopefully you can hear me and you can also see my screen now.
Yes, excellent.
Thank you very much. It is my pleasure and honor of being here. I see this conference as a great opportunity for interactions among the participants and beyond. And from what I have heard so far, I'm pretty confident that the presentations will stimulate discussions afterwards. So my presentation today is focusing cheminformatics, and I would like to first give you, let's say, an overview, a short introduction to this multidisciplinary field of research that is lying mainly at the intersection of chemistry with informatics. And I will try to first highlight some problems that have already been solved, those that are still being actively researched, and of course highlight some of the new challenges in the field. And the rest of my presentation will be focused on 2 case studies from different fields that benefit from cheminformatics. And these are drug discovery and material science, and in particular nanosafety. So starting from the introductory part, let's say, of the presentation, I would like to first define cheminformatics. You can find the term written either as cheminformatics or chemoinformatics, or you can find it as chemical informatics or molecular informatics. Anyway, all these terms refer to the same things, and cheminformatics is defined as the mixing of those information resources to transform data into information and information into knowledge for the intended purpose of making better decisions faster in the area of drug discovery. So it was first born, let's say, invented in order to reduce the time and cost required within a drug discovery pipeline. But it was afterwards, let's say, broaden its domain of applicability to other efforts where large number of compounds are being evaluated for specific properties. So in general, now chemoinformatics is considered as a use of computational and informational techniques to understand problems of chemistry. For instance, the in silico mapping of chemical space, the theoretical space occupied by all possible chemicals and molecules. Nowadays, there is a great number of resources where one could retrieve information related to chemoinformatics. There are numerous books dedicated to this field. There are a great number of scientific journals where the latest and state-of-the-art techniques are being presented. I could name Journal of Chemoinformatics or Journal of Chemical Information and Modeling. And the main question is why chemoinformatics? What is driving the need of advancing in silico methods and tools in chemistry? It is mainly the amount of information for many millions of compounds and their corresponding properties and activities that need to be explored to guide decision making. These data are the starting point. These are could either be experimental or even in silico produced data that should be well organized and searchable within chemical databases, of course. And we need all this data to be fair. You may have heard this term. FAIR stands for findable, accessible, interoperable, and reusable. And if we succeed this very significant first step, then we have made a very significant step forward within our computational workflow. Just to name two of the largest repositories available, including chemical data. The first one is PubChem, and the other one is ChemMBL. These include millions of chemical structures and their properties, their bioactivities, and many more information for its entry. And these databases facilitate a lot the subsequent steps of in silico analysis. So the fact is that the millions of compounds are currently recorded in the aforementioned databases, for instance, the PubChem and ChemMBL. And the questions now arise how to best select the most useful compounds from these used datasets, or how to design new compounds. Chemoinformatics can significantly contribute by enabling fast, cheap virtual experiments to prioritize real experiments, wet lab experiments. Apologies. And what about the physicochemical and biological properties? Then the goal of chemoinformatics is to develop predictive approaches and tools. And for instance, virtual screening is inevitable if one wishes to analyze the huge number of combinations between the available druggable proteins within the human body and the millions of compounds already available within the chemical databases. As I said from the very beginning, from the definition of chemoinformatics, drug discovery and development is one of the main areas of chemoinformatics application. It is, of course, a very long journey to get a drug to the market. That includes several steps from the target identification, drug discovery, development, preclinical, clinical trials, or it includes several steps, phases, and it is of course a very high risk and a very costly and time-consuming procedure. In average, it takes more than 12 years, let's say, and more than $800 to bring a new drug to the market. So we need in silico methods, techniques, and tools to accelerate this procedure in an effort to explore the best therapeutic avenues. And this is particularly applicable, also nowadays with the current COVID-19 pandemic, where several in silico efforts are also in place to assist and complement the current developments. During the past years, we had some significant successes, let's say, and advances in the field, starting from the 2D and 3D chemical representation of molecules, in an effort, of course, to make chemicals machine readable. This is the first major step. So if we wish to in silico explore chemicals, then we need to make sure that our machine can read and store a chemical structure. And this can be done in various ways. Of course, I won't get into much details on this, but it can be done, for instance, by using a line notation like SMILES, the Simplified Molecular Input Line Entry System, or like INGI, which is considered as the digital equivalent to the UPAC name for a compound. Graph theory is also applicable, where a structure can be reproduced with nodes for the atoms and edges for the bonds, or fingerprints are also proposed that encode, for example, the presence or the absence of specific features in a compound, or matrix representations where a structure can be transformed into a table showing different levels of details on the connectivity or distance between the atoms. And now we have, like the examples shown on the slides, we have files like the MOL file or the SDF file that if you're using one of the, or several of the in silico tools already available, you must have used one of these forms. And these are some files that are needed to, in order to submit and read the different chemicals in your data set. And after the structure is made machine readable, let's say, of course, there are many challenges related to that for more complex structures and small molecules. But there is research going towards this direction. We need to convert the structure into a set of useful numbers, the so-called molecular descriptors. This will allow at a later stage, of course, the in silico exploitation of the compounds available. And what these molecular descriptors could be, it could be something as simple as the counting of the number of atoms, including in the structure, or it could be something more complex. For example, the HOMO, the highest occupied molecular orbital, or the lowest unoccupied, the LUMO molecular orbital energies of the structure. So after we have calculated and derived molecular descriptors from the structures, chemoinformatics is a field that deals with the molecules in the multidimensional chemical space defined by these descriptors. After reading the structures and converting this into a set of descriptors, as I have described before, then several in silico techniques can be applied to derive useful conclusion on a specific problem. And these methods include, for instance, de novo design, predictive modeling, molecular docking, molecular modeling and simulation, data mining, virtual screening, just to name a few. And for the next slides, I will particularly focus on predictive modeling. It is one of the most common approaches used in chemoinformatics that is based on the assumption that the property or a biological effect is a function of the structure. And after the structures are translated into numbers, descriptors, the molecular descriptors that I have described before, then all the effort is focusing on identifying the mathematical relationship between the descriptors and the biological activity or property of a structure. And this is where machine learning comes into the game, let's say, because we can use different machine learning algorithms, supervised or unsupervised. I've just put three examples here. For example, the k-nearest neighbor algorithm, or neural networks algorithms, or the support vector machine algorithm that are commonly used in describing this kind of correlations among descriptors and the structures, activities, or properties. So from what I have presented so far, overall a computational workflow includes the steps shown on the slide. First, we need, of course, data, experimental data that could either be retrieved from a chemical database or that could be given by a wet lab. And then the structures included in this data set should be converted into useful numbers, as we said, the molecular descriptors. And then among the available descriptors, we need to select the most significant ones. So we need to run some variable selection algorithms in order to select the most significant ones, and then try to identify the most accurate and robust models based on this data. And these models should be thoroughly evaluated. They should be validated in order to be reliable for a next prediction for a virtual screening. And of course, while building such a model, we need not to forget the domain of its applicability, which is a very important aspect of the model, because we need to know its limitation. We cannot claim that a specific model that was trained based on a specific set of structure could be a universal one applicable in any structure available. And having in hand a robust and accurate predictive model, then we can follow the next step, which is a virtual screening procedure. That is of course less expensive. It is faster than conventional screening because it allows us to scan and screen a very large number of compounds in very less time. And with reduced cost, of course, we have only a computational cost that we have to take into account. And this in silico virtual screening can be done in two ways, either in a structure-based approach where the target is known, the protein is known that we wish to evaluate, and then within a ligand-based approach where we have a set of ligands, a set of small molecules that are known to be active or inactive for a specific target. All these steps that I have mentioned can be combined within a pipelining approach. NIME, for example, is a software which is also freely available and open source that allows the development of such workflows, even by non-programmers, even by non-experts. And NIME allows the combination of the different computational tasks. And it also provides an integrated set of chemoinformatics as well as bioinformatics and general data processing modules. And also, if something is missing, is not there, it allows also the development of new modules. So there are tools available that greatly facilitate the chemoinformatics efforts. I think with this I have finished with first more general and introductory part, and I will continue now with some case studies. The first one is a chemoinformatics edited discovery of small molecules that act as inhibitors of both TNF and RANKL. Both these proteins are related to autoimmune diseases, and for that our main targets to explore new therapeutic avenues for this kind of diseases. I've just played a video from some molecular dynamics simulation that we have run in this case study. And what we did is that we have combined both in silico exploration, let's say, as well as the experimental validation of the results. From the in silico point of view, we have used a variety of techniques, including, for example, molecular docking, data mining, predictive modeling, as I said before, molecular dynamics, as well as several druggability filters that help us eliminate those compounds that do not have the required profile to become drugs. For example, those that do not have the required ADMET properties. ADMET stands for absorption, distribution, metabolism, exertion, and toxicity. And in fact, in this case study, we have used a consensus approach that combines both the structure-based as well as the ligand-based virtual screening process that I have described. So maybe you can see, or maybe not, in more details, the computational workflow that we have used, including these main steps, namely the structure-based and the ligand-based virtual screening. So starting from the TNF crystal structure that is available, and it is we have TNF co-crystallized with an active compound called SPD304. This compound was active, but it was later abandoned due to toxicity issues. We have screened the database, the Maybridge database, that includes almost 50,000 small molecules. And based on this first structure-based screening, we have prioritized a list of 30 compounds. Then we have retrieved data from PubChem databases that I mentioned in the beginning, and there were data available for almost 2,500 compounds. And we have built a predictive model based on this data. And so we have screened these 30 compounds, and we have prioritized a list of 9 compounds for testing. So actually we have shortlisted the available compounds. And these were further evaluated in silico for the RANKL inhibition. And finally, 2 were selected, were validated also experimentally as being dual inhibitors, both for RANKL as well as TNF. And here's some visualization of the interaction of these compounds with the proteins.
Professor Milagraki.
Yes, please.
1 more minute.
Okay. So I'll go through quickly just to highlight the importance of disseminating the model's results, like and in this direction, cloud platforms are available and are of significant help. And just for the few slides on the last case study on nanoinformatics, which is an emerging field of research helping in predicting the behavior of nanomaterials within living organisms or the environment, I would like just to stress, and I'll jump some slides here, to stress the fact that by using in silico tools, we can design and propose several substituents at different positions on a small molecule that it is decorating or used as a functionalization on a given carbon nanotube, for example. So we'll finish with some highlights. First of all, that chemoinformatics is a multidisciplinary approach. So we need experts from different fields, from chemistry, physics, biology, material science, and of course, informatics. Advances in machine learning and artificial intelligence, but also cloud solutions and application program interfaces, APIs are significantly contributing in the field. And so far, we have several examples appearing in the literature where chemoinformatics has contributed to a wide range of applications within several research areas, such as computation toxicology, drug discovery, and nanomaterials risk assessment. I will be very happy to answer all your questions in the noon session, I think, with the Q&As. Thank you very much for your attention.
Thank you very much, Professor Milagraki. If you can switch off your screensaver. I am sure you realize that for us who are in chemistry, in the future, what we call reaction mechanisms will be changed into chemoinformatics.
Yes, that's true.
I would be very happy if you would be available during the Q&A session for questions.
I will be for sure. Thank you, Professor.
Thank you very much. Now, we have a short break. We should be back at 11:50, 12 to 10, for the second part of session 1. And in the meantime, I think we can have our sponsors on our screens. Please come back at 11:50. Thank you very much. The second part of session 1 of the conference manage his creations. I think we are all here. The next speaker is Professor Papadakis from the Greek Army Academy, who is going to give a speech with the title Towards Information-Driven Cybersecurity using Scalable Machine Learning. Professor Papadakis, please go on.
Thank you, Mr. Chairman. And I would like also to thank the organizers for giving me this opportunity to present my work. And just a minute to share my screen.
We can all see it, I think.
Yes, okay. So my name is Nikos Papadakis. I'm assistant professor at the Hellenic Army Academy, already covered by Dr. Mouzakis. The Hellenic Army Academy, or SSE in abbreviation after its Greek name, is a multidisciplinary institution covering all major academic disciplines like mathematics, engineering, security, cryptography, languages, history, artificial intelligence, robotics, and so on. And also it is among the 10 most prestigious military academies, currently holding the 8th position. So my speech is about cybersecurity and cognitive machines. That means how to use artificial intelligence on cybersecurity. And I will be presenting the Palantir solution. So first of all, we are participating in a European funded project, Palantir, with the Hellenic Army Academy, with the Laboratory of Machines, Intelligent and Distributed Systems. That is a laboratory that newly established. It has been founded 3 years ago. It is heavily involved in the implementation of several national research projects and also this particular European funded project. It covers many research domains like machines, artificial intelligence, cognitive cybersecurity, robotics and self-driving vehicles, natural language processing, computer vision, and big data analytics and IoT. So what's the problem? The problem is that we know that there are a lot of cyber attacks, and the tools we have to defend against those attacks are somehow, let's say, obsolete, because they are rule-based. That means they rely on signatures. They have a database with known signatures, known signature of threads, and when a thread is presented somehow, they are able to identify this thread and eventually take the appropriate measures. So we have intrusion detection systems, intrusion prevention systems, antiviruses, logic systems, and so on. All these systems are rule-based, are signature-based, and they deal with the known knowns. That means the things we know. But there are also knowns. There are also known unknowns. That means to say are things we don't know. We know that we don't know, and there are also the unknown unknowns. That means there are things that we don't know. We don't know. So these two cases of known unknowns and unknown unknowns are by definition not relevant to the solutions we have right now. Sorry? Yes. The consequences of cybersecurity are well known. The problem is that existing solutions need to wait for something to happen before reacting to it. And this causes also an elevated cost of damage to medium or large enterprises. In the last 5 years, on average, this damage was increased by 72%. And each year it rises about 12%. So this is the problem, and we have to find a more intelligent, let's say, solution to the problem. And here comes the artificial intelligence to cover this need. The problem is not only related to large corporations and huge institutions and so on, but also concerns the small, medium enterprises and also the micro enterprises. Many times, very often, they are the route to the bigger prize, that means the larger enterprises. And the damage to these companies is also it's about 35,000 euros per incident. That's a huge amount. So what's the solution? The solution I will be presenting today is based on Paladir. Paladir is a European funded project, and it uses hybrid threat intelligence, combining both machine learning and deep learning models, along with virtualized signature-based intrusion detection systems and other, let's say, systems we have today. This solution deals with the known knowns, but also with the known unknowns and the known unknowns. So it's a solution that can be deployed in also in future problems that we don't know right now. Paladir is, as I said before, a European research and development project. It was funded under the Horizon 2020 framework. It is a consortium of 15 partners, has a duration of 5.2 million euros and a duration of 36 months. Participate, as you can see by the logos here, industrial partners like Hewlett-Packard, NEC, but also Telefonica, and also research institutes like I2CAT, Demokritos from Greece, University of Murcia, and of course Hellenic Army Academy, as stated before. So Paladir builds on risk assessment, virtualization, closed loop control, machine learning, and remote attestation. And here I present a brief, let's say, a consistent architecture of the Paladir. It has many modules and components. The major 5 modules are depicted here. The first one is the threat intelligence. That is the module that collects the traffic, analyzes it, and reports eventually threats, and suggests also the remediations to take in order to mitigate, let's say, the problem. So the second module is the security service orchestration, containing several other components like the security orchestrator, the service orchestrator, etc., that acts by materializing, in a sense, the security threat to security actions by selecting a set of security as a service solutions, the appropriate each time. So it consists of virtual firewalls, virtual antiviruses, virtual deep packet inspection components, and so on. The fourth module is the trust and attestation module, that is runtime hardware and software attestation to verify the integrity of the system, and manage also the fault that may occur in both in software and hardware, but also data breaches and so on. The fourth component is, the fifth component is the risk-based analysis. It is, let's say, the module that personalizes the elements of the architecture based on the calculation, the risk calculation for each individual small, medium enterprise company. So concerning the threat intelligence, and this is the work that we mainly focus at our laboratory in Hellenic Army Academy, consists of several also steps and components. If you can magnify somehow this module, will find components like pre-processing and sanitization that act by cleaning somehow the data flow. And then we have two separate steps. The one is the anomaly detection that uses deep learning techniques and deep learning algorithms to define and to find what is abnormal, what is beyond, let's say, the normal operation. And then we have the second step, that is the threat classification model, that somehow is the classifier that identifies the kind of the type of the anomaly. Two-phase approach using machine learning and deep learning. The first is the anomaly detection on network traffic to detect malicious behavior and to pass it to the second phase, the classifier that detects the anomalies to specific threats. And then, of course, we can have the appropriate measures to deal with the specific problem. To do so, we employed an algorithm that is commonly used in textual corpora. It is the LDA, latent Dirichlet allocation. This actually is a topic model. It is an algorithm that from several documents of text, for instance, can identify the topics that are related to each document. And of course, also the topics that are shared among all these documents. So in our case, we don't have textual corpora, we have network traffic. So somehow we have to transform the network traffic to text, to words, and of course to documents. So we have now the notion of document that corresponds to an IP address, and also the words that are related to log entries, and the topics that they have to be matched somehow to the profiles of common network activity. So we have 5 distinct steps here to follow. The first one is to convert all network log entries into words. I will show you how. Then treat all the network logs, the words, to correspond to the same IP as the IP document. Then start topic discovery inference and assign a mixture of topics to each document given its content. Of course, it's traffic, it's specific traffic. And then finally calculate the likelihood of a new word belonging to a document based on topics mixture. So low likelihood means suspicious activity, because this means that it is something not normal, not shared among a lot of other documents, let's say. In brief, in order to create this word, for each log, in each log we have the date, we have the time, the duration, the protocol involved, the network protocol, the source IP, the source port, the destination IP, the destination port, the bytes involved, and the packets. We have established a set of rules in order to create, let's say, the syllab of each word. So the first syllab always concerns the flow direction value, and we have some rules in order to create this syllab. In this case, since both IPs are using ports less than 1025, it's -1. The red one, the bottom of the presentation, of the slide. The second syllab is somehow governed by the key port values. That means the source port and the destination port. In this case, is 301 based on the rules we have. The third syllab is the protocol itself. The fourth is the time value. We get only the time, not the seconds or the minutes. Then the byte values that are a value related to the pins we have that are also related to powers of 2. So in this case, we have 1026 bytes. That means 2 in the 11th power. So we have, considering also 0, the 12th bin. And so we have created 2 words, one for the source IP and another for the destination IP. They may be different or maybe the same. This way, we can create the document for each IP. And then we are able, through the LDA, to calculate the likelihood of each log to belong to the topic mixture of each IP. So large likelihood means benign network activity. Small likelihood means anomaly suspicious network activity. We also, for this first step, the anomaly detection model, employ also other algorithms like autoencoder, one-class support vector machines, isolation forests, and so on. This is an unattended procedure is unsupervised machine learning, so we don't have training data or anything else. The system has to configure itself by the network it sees, by the knowledge it accumulates by following the network that it monitors. The second step, that is the threat classification model. Here we use random forest algorithm, but also multi-layer perceptron and CNN RNN algorithms. So we have tested our algorithms with several attack types, like DDoS attacks, distributed denial of service and denial of service, through by generating corporate data sets in a sense that are somehow labeled with DOS attack or data exfiltration.
Oh, I can see everything now. Beautiful.
And crypto mining.
Right. I'll wait for your instructions when the speaker is finished.
Yes. Also, we had the opportunity to test our cases with offline benchmark datasets. One of them was the CI/CIDS 2017. It is a dataset that is available. It's publicly available through a company UNP.
One more minute, please.
Yes, I'm including. Yeah, and these are the benchmark datasets. So we have tested our processes, and we found that the accuracy, precision, the record are very, very good in our case. And since we don't have other means to determine unknown unknowns, this is, of course, something that is very, very important. The same happens also for the results on the classificator, on the classifier, on the classification part. Accuracy, precision, the record are very, very high, as you can see here. And also some preliminary results on encrypted traffic classification are very, very promising. So this slide concludes my presentation, and of course I will be available for any questions.
Thank you very much, Professor Papadakis. I hope you will be able to join us during the Q&A session.
Yes.
For questions and answers.
Sure.
If you can switch off your screen share.
Of course.
Now, dear friends, we have a request from Yale University, so we will make a short break before the next presentation. We have on screen Professor Sten Vermouth, Dean of Public Health of Yale University and United States of America. It's our great honor to have you with us, Professor Vermouth. Please go on.
Thank you so much. I hope you can hear me okay.
It's very, very nice. Go on, please.
All right, very nice. Well, thank you very much. The Athens Calls Athens Conference is an important contribution. We're really absolutely thrilled to participate. Two of our faculty, Dr. Kyriakidis and Dr. Vasiliou, are participating actively. One of them comes from Cyprus and the other comes from Greece. So the American tradition of talent that comes from abroad continues. My own parents were immigrants from Norway. We are very concerned about the state of public health in the world today. We've had tremendous challenges in the past year. Among these challenges includes the coronavirus, COVID-19 pandemic. And in the US, we've also had the awareness of the social determinants of disease, particularly race, and how race can sometimes determine clinical outcomes. We've had examples of systemic violence against persons of minority background. So we're wrestling with fundamental challenges in public health, and your conference could not come at a better time to review the challenges in prevention, the challenges in screening and clinical care, the challenges in society that can help us tackle the major issues of our day. So we're all aware of the pandemic threats. Some countries have done better in coping with those threats. Greece is one of them, Norway is another. Other countries have struggled. For example, Spain and the United States. So it will be important for us in this conference to discuss why are there these differences in response to pandemic threats, preparedness, why were some countries better prepared and better able to control the outbreak, such as Greece and Norway, other countries not so well prepared, such as Spain and the United States. I would urge you, as you deliberate, to also look at the other great challenges of our day. For example, we have the climate change and global warming, which is an existential threat to humanity. We literally see islands disappearing, people having to be relocated because of the rising ocean levels. And it's a vicious circle when the glaciers and the snow melt in the Himalayas are diminished. We have more rock showing and more absorption of sun and an acceleration of that process. Let's take the Indus River, Ganges River, Brahmaputra, and Mekong River basins. There are about 1.5 billion people, 1.5 billion people living in those regions. And when we disrupt the ecology and the snow patterns of the Himalayas due to global warming, we will have terrible cycles of drought and flood, depending upon the time of year, in a catchment area of such a tremendous number of people. The desertification of the Sahel region with the Sahara Desert growing, the chopping down of the great forests of Burma and the great forests of the Amazon, all of these things are going to threaten the livelihoods and the health of our grandchildren in a very serious way. So public health needs to be on everyone's lips these days. Prevention needs to be something that we acknowledge as a top priority. And we're going to need the consultation of people from diverse disciplines. We're going to need our social and behavioral scientists. We're going to need our philosophers and historians. We are going to need our political scientists and economists, in addition to the epidemiologists and the health systems experts and the experts in climatology and meteorology, all of us striving to resolve these urgent and necessary agendae. The theme of this year's conference of Athens Calls Athens is a very suitable one. I believe that you're holding this conference in October of 2020 is a historic moment. And I believe that the fact that you've recruited this international pool of presenters and a tremendous number of sponsors. I'm very proud that Greece is hosting this, because Greece, of course, has its history nested in the founding of Western civilization. The Greeks have coped with every imaginable philosophical and practical problem over the millennia, and we're going to need all of the creative talent and leadership of your country to join the folks in the rest of the world to resolve these tremendous public health emergencies. So without further ado, I think I'll turn it back to you to continue the conference. And thank you very much for giving me the opportunity to make a few of these comments. I had taped some comments, but we had some technological difficulties, so I'm glad I was able to join you live.
Thank you very much for your nice speech, Professor Vermont. We have to understand that if we stop destroying the environment now, it will take a few decades when it comes back. And everybody has to understand that, ordinary people, not only scientists. Thank you very much. If you want to add something, you can do that, but thank you very much indeed for your presentation. Bye-bye.
My pleasure. Thank you.
Now we can now proceed with the lectures. The next lecture comes again from the Greek Army Academy, Professor Litke. His lecture, the title is Blockchain and Smart Contracts for Internet of Things Applications. Professor Litke, please go on.
Thank you very much, Professor Kalakirinos. I would like to thank also the organizers for giving us the opportunity to present our research work. As said, my presentation today is about blockchains and smart contracts for Internet of Things applications. It's structured as follows. I mean, we are going to see a brief overview of blockchain and the integration with Internet of Things technologies, the need, some indicative use cases. Then I'm going to get a little bit deeper onto some particular use cases that come from MSEC EU-Japan project, how there we are experimenting with design and implementation of Internet of Things marketplaces assisted by the blockchain technology, technical issues that have to do with how to integrate Internet of Things sensors and what kind of use cases these technologies can facilitate. Some further research issues, and of course, the conclusion of the Q&A session. I mean, some of people know about the blockchain, which is actually a highly distributed ledger, a data structure which is shared among different peers of peer-to-peer networking infrastructure, and it is actually a data structure that is concurrently shared by all those participants, and which actually facilitates different transactions, different interactions between those participants. There is a distinction between those distributed ledgers. We call it public permissionless blockchains, which actually are totally decentralized in the sense that there is no single authority actually managing the specific infrastructure and controlling it, of course. And we have also permissioned blockchains, which means they are also called consortium blockchains in the sense that there is an authority which actually gives the authorization for someone to participate there. And all of them are synchronized. This data structure, the challenge is to have this data structure synchronized in such a way that all peers in the network have a common view of all the transactions, which makes any central authority for keeping these records obsolete. So there is a variety of use cases that actually blockchains can support and facilitate and provide a path to business value. Financial agreements, supply chain management, for instance, where we have the ability to have a transparency on this blockchain for all actors, for all stakeholders that participate there and share information on the different goods and items that are produced or transferred in this logistics chain. Financial technologies, of course, what we call the fintech, other smart contracts for the legal issues that can be automated on those blockchains, encoded as smart contracts and be executed in an automated way. Other aspects of Internet of Things, like for instance, smart grids, and we're going to see an example, digital rights management, and so on. Just to give the example how it works on smart grids, for instance. We know that there are the smart meters, and those smart meters, the utilities, like for instance, if it's for an energy company or for a water company, for a water supply company, they have the ability to capture and remotely transfer the specific usage data. So just to give an example, those smart meters can be integrated through, can be tagged on those blockchains and actually provide those data, those measurements they are having on the blockchain structure. As you can see, this then is going to produce a transparent way to, for all participants, for all stakeholders to have access on those data, given of course that there are some particular needs for privacy, anonymization, and so on. And then it comes where, as you can see here, this blockchain, what we call the distributed ledger platform, can be the basis for different existing stakeholders or new stakeholders to come have access on these data and form the basis, for instance, for peer-to-peer trading between all those participants, to form a marketplace and actually a decentralized exchange facility so that other players, governments or manufacturers or even new players, we're talking about the open innovation, how new entrants can come and provide new services, new business value on those data. So smart grids have a lot of common also with the Internet of Things, because as you can see, they are relying also on smart objects, smart meters in this case, which can produce data and utilize them for further opportunities. So to this end, I would like also to present you a specific project. It's called MSEC. It's a project funded under Horizon 2020 program, which is an EU-Japan collaboration. And there we participate through a team of the National Technical University of Athens. It's a consortium from Japan. It's a consortium from Europe. And as you can see, the mission of this project is actually to develop an end-to-end secure Internet of Things platform, facilitated assisted by blockchain technologies where different stakeholders can build innovative smart city applications and create new business model for those IoT stakeholders. As already said, the main pillars, the main market drivers, if you prefer, for these is on one side, the increased use of Internet of Things. We see that also from the previous speakers, we talk about autonomous vehicles, we talk about smart city applications, a widespread use of the Internet of Things technologies, which make things easier for this. And at the same time, we have other technology advancements, like, for instance, artificial intelligence, blockchain, as already said, machine learning, and then there is a good opportunity. So one of the main objectives of this project is actually to create this decentralized IoT ecosystem, to create the ecosystem where we can validate the viability and sustainability of these specific examples we can have for the Internet of Things and blockchain. Smart objects can exchange information, energy, and services. And for this reason, there are two major pilot sites. The one is in Santander City in Spain, and the one is Fujisawa, a broader metropolitan area in Japan, which acts as a pilot for validating the specific things we have developed. Indicative, I will not go into details. There are various use cases that are being examined in the specific project. Just to give you some example, a use case which is operated in Fujisawa, which has to do with secure and trustworthy mobile sensing platform. There they have the garbage collecting trucks, which are equipped with different sensors. They monitor environmental conditions like air quality, temperature, humidity. And this, as you can understand, is a dynamic Internet of Things network which shares measurements. At the same time, there is a challenge to increase the privacy. So we couple there also edge computing principles that have to do with the first filtering of the data that have to be provided on the blockchain. Another use case has to do with secure and effective participatory sensing of city. There, we deploy also mobile applications that is the other pillar, if you prefer, of the Internet of Things widespread opportunity, where humans, through their mobile devices, can act also as sensors, human sensors. And they can capture pictures, they can, let's say, generate data that can be part of a further, let's say, Internet of Things data stream that comes into play. And we have also what already said, the smart city data marketplace, where we have there a unique way to combine all of this data into something called a marketplace, where we can exchange and we can share value through the different data. Of course, we talk about open data as well, but it's important to underline that there is a big value on proprietary data, that there is a new way now to monetize on them. How this marketplace is being built. So on one side, there are different challenges, like for instance, to build the different smart contracts, pieces of code which is going to be deployed on the blockchain and which is going to be executed in an automated way when it comes time. We have developed this on Quorum blockchain, which is an Ethereum-like blockchain with increased features on privacy and security. And to this end, we have deployed all those necessary middleware services, like for instance, know your customer processes, because after all, there is a share of exchanging value. Even of course, it's a research project and there is no actually mapping to real value, but on tokens that we have created as crypto coins only for experimental purposes. And there are a lot of challenges, like for instance, how we are going to wire all together the different services, how we can orchestrate them in such a way. Different technologies have been deployed, like for instance, Node-RED, for all those application-specific workflows that have to be programmed. Different data sources that come also from platforms which aggregate data from data streams throughout the smart city, like for instance Foxfire, which I'm going to detail a little bit later on, and of course other open data sources that have to do, for instance, with weather conditions, where we can acquire and bring them together in this value formation on how we can use those data. And a plethora of different smart contracts for those who are more familiar with the blockchain technologies, how you can encode things and put them on this blockchain for being executed later on in an automated way when the time comes. A very interesting approach is our synergy with the Keio University of Tokyo, where they have the Foxfire platform, which is, as you can see here, a platform that aggregates data from different Internet of Things data streams throughout the city, as already said, also from the garbage collecting trucks they have. And they use a middleware platform based on public subscribe principles that actually gather the data. And for us, from Japan to Greece, there is, from our side, a proxy server implemented, which gets this data and transforms them into transactions on the blockchain. And all of this is trying to create the whole value chain of how we acquire data from even very remote places and try to provide them as an input on those infrastructure. At the same time, we are experimenting also with other features that we would like to see being implemented as part of the different validation mechanisms for the blockchain. We have experimented in the frame of this project with a proof of location mechanism, which actually, because I've given you the example on how also users through their smartphones are producing data in this smart city context. And there is a big opportunity to identify ways where the data captured from those mobile devices are verified, in the sense that, yes, there is some, let's say, certification that it's a true picture taken from the specific mobile phone. And to this end, we have developed a mechanism which is based on ultrasound techniques to have another proof of the validity, which has to do with the proof of location protocol and strong identities on those people who actually capture the data and provide them in the blockchain. And we're experimenting also with increasing the security features on the blockchain, because after all, as I said, blockchains are distributed ledgers. So typically what is written there cannot be removed. So this is a very important factor for us to experiment with different technologies that can give us better abilities on how we can manage those data. So what we have done is also create some a new blockchain model based on graph databases, because graph databases have many features and many abilities to handle the data and treat them as graphs. So applying a lot of theory from those graph models and experiment with the consensus protocols. And not only that, experiment also with analytics on those blockchains. Because once you have the different transactions modeled as nodes in a graph, then there are a lot of further abilities you can have to analyze them, define different metrics that you would like to experiment with, and increase various features of the blockchain, like for instance, security mechanisms and attacks that you would like to simulate and have a better view. So, as a conclusion, which I would like to highlight here in this speech, is that we can see that there is a good opportunity for integrating blockchain technologies with Internet of Things mechanisms, principles, approaches, methodologies. So we see that there is an ongoing trend to go from the Internet of Things, which is a term that was coined almost 1 decade ago, to a new concept of Internet of Value. So not only having smart objects, but having those smart objects being able to interact with each other and exchange, share value. There are, of course, this will enable new modalities for autonomous interaction. So there is also the tendency that we go from the smart things to socially smart things, because then the smart objects will be able to, based on the value they're going to share, form their own social relationships and interact with them, if we can call them, of course, social. Of course, privacy and identity management, as well as security issues, have still a lot of work ahead. And this is something that the research community, as we can see also, is focusing on and trying to provide different solutions so that we increase all this for the benefit of the human actors. So that's all from my side. Thank you once again, and I'm happy to take your question also on the Q&A session. Thank you.
Thank you very much, Professor Ritchie. In other words, we cannot live without internet anymore. This is what I understood. The next speaker for today will be Professor Kalles from Hellenic Open University, who is going to present to us a lecture with the title Artificial Intelligence, Learning About AI, Artificial Intelligence, Without Fearing. Professor Kalles, please go on.
Thank you, Mr. Chairman. I'd like also to thank the organizers for inviting me to this conference. And I'd also like to acknowledge the spirited talks from my fellow speakers. Now, I will take a minute to share my screen, and I would like to have an indication whether my sound is loud and clear and the screen comes through clearly.
Is it possible to have the microphone a little bit closer to your mouth?
How about now?
Excellent.
Right, thanks a lot. So I'm an associate professor of AI at the Hellenic Open University. I've been doing research in AI since my PhD years in the UK about 30 years ago, which means that I now enjoy that this field is becoming a bit more pronounced than it has come out of the obscurity that it used to dwell on, let's say 2 or 3 decades ago. And I'm really enjoying that. I'm also a member of the board of the Hellenic AI Society. And my talk for today is going to be about a brief perspective of AI, a brief historical perspective that will allow us to put it into the context of today's life. The underlying theme about learning about AI without fearing it has to do with the news that we're getting every day about AI applications and the hoopla about AI taking over our lives, which, according to my view, is not going to be the case. But let's get on with the talk. Now, we've been hearing from some of the speakers in this session that as of the middle of the 20th century, we've been witnessing a lot of industrial innovation. And I'd also like to draw your attention to that date, 1956, when some very high caliber researchers convened in Dartmouth in the United States and set out their vision about this new field. That's when the AI term was coined. Now, if you look at what they were having as a vision, that's pretty grand. We're not there yet. And if you put into perspective the arrogance and the ignorance that the new field is bound to have, I'll let you know that some of these founding fathers of AI thought that 2 or 3 months of a graduate project might be enough to solve problems that we have still trying to attack without huge success. So 60 years on, and billions of dollars and euros of investment, and thousands of man years of research time, and still the vision is not there. So what a challenge we've set ourselves. Now, well, we've set this huge challenge mainly because we have not been calling it AI. but mankind has been doggedly pursuing this topic. So we were not calling it AI, but we were trying to deal with, let's say, the systematization of thought processes. So if we go back 2,500 years with Aristotle, who had thought about casting, planning as information processing. And then as mankind was coming out of the European Middle Ages, we had Ramon Hall, who was a polyglot, a philosopher, a theologist, an engineer, you name what. You know, the Renaissance people that were able to do everything. He also tried to create a mechanical way of creating new knowledge. Now, if that's not AI, what is? And then I'll draw you back to the start of the 20th century, when the great dispute
Do you have any PowerPoint? Do you have any PowerPoint?
Well, I am sharing it. Is it not shared?
No, you have to share the screen.
Apologies for that. I'll take just a minute to do that again. I was under the impression that this was being done. Sorry about that.
Down on the screen. Okay, that's okay. That's much better. Thank you.
Thanks for alerting me to that. Let me now. Well, you didn't lose too much out of slides action. So what I was referring to was that in the early 20th century, we had a huge row in mathematics, a huge dispute between two great people, Hilbert and Poincaré. And Hilbert's idea was that one might be even able to use mathematics to describe everything about mathematics. Now, I'm not going to deal with that part of history, but suffice it to say that this gave rise to computing. Now, one of the primal fears that we have as people about artificial intelligence, I think stems from the fact that we really, most of us, cannot really describe what intelligence is. So while if we look around, we can acknowledge intelligent behavior, we feel pretty confident we can do that, we are still unable to describe it. And if we look at ourselves, we may feel confident that we can act intelligently, but we can very often observe ourselves not doing so. So this is a big contradiction, and I think contradictions reflect things that we cannot understand, and that's where our fears are based on. Now, for us AI scientists, we set a bit lower targets, and we are trying to quantify things so that we can arrive at a convenient definition for AI. So instead of going for something that is intelligent, we are going for something that demonstrates behavior which somebody, an expert, could consider as being intelligent. For example, if we can create machines that can win a lot of chess games against human opponents that we deem to be experts, then we can convince the audience at large that this machine demonstrates some intelligence, because all of us tend to agree that chess masters are smart people. So basically, we are constraining ourselves so that we can show some progress. But that's how science always goes on. We set ourselves a lower goal, we achieve that, and then we move a step upwards. Now, a coarse map of AI is that we tend to classify systems along two major axes. One of the axes is about how systems seem to act. And about another axis is how systems tend to think. The upper right quarter is systems which act like humans, and that's where most of the applications sit. And what better application to describe than the one that masters the news for the last, let's say, decade, the autonomous driving applications. So Waymo was a Google subsidiary that dealt with autonomous vehicles. But I'd like you to have a look at the left part of the screen, which is research that was funded by the US Army and I think carried out in Cornell, where people were experimenting with autonomous driving vehicles. So even if they set the basis for a lot of the technologies that we're using today, it was more or less primitive along a variety of directions that today, dimensions that today we have advanced. But it was still there 25 years ago. So my main point here is that as we are witnessing a lot of AI hype and news today, what we're actually witnessing is that AI is the icing on the cake. We have a lot of technologies that have matured in parallel to AI, and it's the convergence of these technologies that allows AI today to be in such a prominence. So it's not on its own. No technology is good enough on its own. I'll also give you another view of the context. Since the 1990s, you may also all have heard about Moore's law, about performance doubling every 18 months or so. Well, this is a rule of thumb estimate, but if you take this doubling over 2 decades, then you see computing performance at huge performance levels, which allows us to tackle problems that 20 or 30 years ago we were toying with. And another point of view that you need to look at is that there has been a steady flow of private investment going into AI, recognizing its huge potential. But this private investment grows more rapidly and has started much later than the public investment. The public investment since the 50s has channeled its way into research, into universities, and into the basic technologies that power most of AI today. So I'll now give you an example based on this timeline about neural networks. You may all have heard that neural networks are, or deep learning, are, let's say, the holy grail of how to apply AI to any given problem. Suffice it to say that in the 1940s, we already had an idea of how a basic calculating machine or a basic computer could be built using, let's say, neurons, perceptrons, very simple models of how the brain works. Now, these 1940s gave rise to some research on neural networks, only you've never heard of that. You've never heard of that because some very bright people in the 1960s and 70s, late 60s, published some research that demonstrated the fundamental deficiencies or weaknesses or limitations of these machines. However, these limitations gave rise to, let's say, to the imagination of really bright people who in the mid-80s started dealing with the mathematical foundations of neural networks. They have proved some excellent properties about neural networks being universal function approximators, and that unleashed, let's say, a wave of new research, of funding, which in the 1990s gave rise to the autonomous driving prototypes that I have described you. And 20 years later, we have Uber roaming our roads, and we have AlphaZero, which is a generic learning machine that is able to beat human champions at the level of, at the game of Go 20 years after having beaten Kasparov at the game of chess. So what I'm trying to drive my talk at is that nothing happens overnight. You need to monitor the scientific progress over decades and over generations until things converge together. And still, neural networks, for all the hype, have a fundamental deficiency. It's very difficult to explain them. I'll give you an example. Now, assume that somebody goes to a planet and they are given some information about who is male and who is female in this planet. And then this strange orange creature arrives and you need to decide its gender. Well, for us humans, it's pretty obvious. We're going to try to cast these figures in terms of eyes, legs, colors, you know, things that we know we can describe. But there is an easier way. You can go to Google's teachable machine. You can say, I've got 3 examples of class 1. That's the upper row. I've got 3 examples of another class. That's the bottom row, class 2. And I've got an unclassified sample. That's the big image on the right. And please tell me what it is. Well, it will tell you it's class 1. Now, is it class 1? I would say yes. And here's the reason why it's class 1. Well, it's not very explainable though, yeah? Google is just going to give you it's class 1. However, what we did as people was try to figure out the number of legs, number of eyes and colors, things that we know we can identify, even though it may not be straightforward to describe what they mean. So giving meaning to things is something that we humans are accustomed to do it. Neural networks cannot do it. You seldom hear about data, but this is one of the reasons that the news will let you know that AI will take us over without us realizing that. Let me put that back again into perspective. I think AI is going to be just one thing, as some of the fellow speakers have already said so, in the, let's say, grand scheme of things. We can review printing, steam engines, cars, antibiotics, anything. AI might be a place, a point in time when the future historian will decide that it was important or not. Maybe not AI, maybe an application that AI empowered. For example, robotic justice. The key question is who has access to these technologies, who benefits from them, how much does it cost, who sets priorities. I think these are the questions that will shape the answer we will give to whether AI is going to be used for our good or against us. For example, also I have 3 nice pictures here. One of them is Kasparov's match against IBM's Deep Blue. Is that going to be featured as a time point like the press? I don't know, maybe. The self-driving cars, and I also urge you to Google the next Rembrandt, which was a joint project by AAG, the Dutch insurance giant, and Microsoft, who jointly analyzed several hundreds of Rembrandt's paintings and came up with a new painting that looks like a painting that Rembrandt could have painted. Now, that's AI, and that could be the shape of things to come. Now, as I'm approaching the end of my talk, I'd like to remind you that AI is not the same to all of us. To the trained scientists and to the engineers, AI is something they can understand, they can explain, or they can build. For the people, AI is a double-edged sword. It can have good applications and it can have bad applications. It's the press that gets to decide how to paint an application. And I think that scientists and engineers should have more say over how the press describes their work. I think what we're witnessing right now is the industry's view, not the engineers or the scientists' view. The public needs to know what we scientists think about AI too. Here's a scenario. What is the end of the road for autonomous vehicles? Let's say 20 years from now, will we be needing taxi drivers? Maybe we're going to be needing driving companions. Maybe the word companion is going to be a beneficial word. It's not going to be a vicious one. Will I have to work on my way to the office? Will I have free time? And who is responsible if I run over a person? Now, I think that's, again, one of the fears that we're having. The fear about losing controls of our destiny. As I said again, I think that the press has to be trained how to describe AI so that this fear does not grow. So what should we be doing? What I'm showing you right there are the 5 takeaway messages that a committee working under the Obama administration delivered about the strategic approach of the United States to AI. If you look at that, it's just the first item that's the long-term investment in science. The other 4 items are about how you integrate AI into the everyday life of people. It's not technical. It's mainly political, economical, and social. And the Obama administration paved the way for all other big players to do something like that. In 2017, we have what the People's Republic of China delivered on AI. They have a grand vision until 2030 to be the premium AI power in the world. And then last year, the OECD and the European Union also delivered the same guidelines. So I'll leave it to that. That's what we should be doing. That's what the major players converge on believe we should be doing. And only one bit of it is scientific research. The other is how we make that research relevant to the people. Thanks a lot for bearing with me. I will be happy to take any questions.
Thank you very much for the excellent speech. Now we have a last minute presentation for today by Mr. Panagiotis Stefanidis, who is a mechanical architect. He is also a mathematician and a philosopher. The title of his lecture is Proposed Architecture of a Model Optically Tracked Satellite based on the geometry of a recently invented solid form, the generator polyhedron, related to the philosophy and geometry involved in structuring the 5 Platonic Euclidean polyhedra. Mr. Stefanidis, you go on for the next 20 minutes.
Good morning, Professor Kalokerinos. I thank you and the organizing committee for my presentation here. My work involves...
If you have a PowerPoint, you can share your screen.
Can you see me?
We see you. If you have a PowerPoint...
I have the PowerPoint on.
You go on, press share screen. Down on your screen. Down on your screen.
A minute, please.
You press share screen.
Share screen.
The green button.
Give us a minute.
Just a minute, Professor.
Okay, share
it-
screen.
Down on the screen, it says share screen, a green button.
Cannot see it yet.
No?
You see that? Share screen, you press it. Excellent.
Okay, thank you very much,
Okay,
Professor.
okay, go on.
This work concerns a new polyhedron, and the name is generator polyhedron, a proposed architecture of a model optically tracked satellite based on this polyhedron. This is a non-regular icosahedron related with the Platonic polyhedra, icosahedron, and dodecahedron, etc. This, for instance, is a regular icosahedron. Now we talk about this newly invented polyhedron. This futuristic architectural proposal is based on a very special geometry of a recently discovered invention of a non-regular icosahedron, related geometrically as a whole to the 5 Platonic Euclidean polyhedra. The model built has 12 isosceles triangles and 8 equilateral triangles. Mirror triangles, cut to size, invested the structure of the configuration of a polyhedro heliotrope satellite optical tracking application. Homemade darkroom for satellite space simulation involved for photos and video clips taken. The skeleton structure of this polyhedron consists of 3 orthogonal parallelogram planes vertical to each other. Generator refers to the geometric characteristics of this non-regular icosahedron found to be roots of the Platonic Euclidean polyhedra. It is related to the icosahedron, which in turn relates itself to the dodecahedron of involved sides dimensions of their original parallelogram skeleton plane structures in the ratio of phi square by phi for the dodecahedron to icosahedron, and phi by root phi equals root phi for the icosahedron to generator polyhedron. Further important angular relationships between dodecahedron and generator polyhedron found on this relationship. 1 over sine 54 is this number which we find in the generator polyhedron as well. Space simulation using a homemade darkroom. This polyhedron built and a darkroom was used, a homemade darkroom, so that I took this video. Now another simulation is this one. Now we see the triangular faces in space simulation, of course, and due to the varied triangle areas, the two kinds used, the light energy received is different. So it's a form of satellite codification. Now this is a space simulation photo also of the polyhedron. The skeleton structure of this polyhedron consists of 3 orthogonal parallelogram planes vertical to each other of side 4p by area, and the sides ratio 4 by p equals root phi, square root of the golden section, where for p is used this number. The geometry of this work is part of a published book of mine, which I call Treatise on the Circle, and finally, finalizing the book, I came to this polyhedral structure. Now, this is the structure of a regular icosahedron, and this is the plane, the blue parallelogram is the skeleton plane. 3 of these vertical to each other form the skeleton of the icosahedron. And if you see, there are 1 triangle, 2 triangles, which belong to the face of the model of a great pyramid. So from this face, we go on building the polyhedra. This is another photo showing this parallelogram and the model of the Great Pyramid. Now this red, blue, and this square, round quarter of the pyramid is using some forms of tetrahedra. The red one is the main tetrahedron that builds the pyramid, and stereoid according to Plato's proposal and my interpretation. These are the 3 parts of this quarter pyramid. Also here the same. Now here I have used 35 years before I interpreted Plato's most beautiful triangle in a different way than the current publications and interpretations use. This is a triangle whose product AB times A alpha gamma equals B gamma square. Under this triangle, theta gives the sole property of this triangle, and worked on this, its theory. Now this is a ruler and compass from KLM triangle under phi golden ratio. We receive theta by ruler and compass of the triangle L and M, obeying this t to the 4 minus t square minus 1 equals 0 equation. Similarly, here we have this triangle within the circle, and we have alpha, beta, beta gamma, alpha gamma. The product of beta alpha times alpha gamma equals beta gamma square. This is an area. And under condition that alpha, beta, we call it P, we don't know what it is here. We have that P or pi times the diameter is the circumference. And actually pi times the diameter is the square of this beta gamma, which is the area of gamma, delta, epsilon, beta. So we have in fact an area related to the perimeter of the circle. This is another model which I cannot see well to show it to you, but it relates the circle circumference and circle area with a square area, which was impossible for the past. Apparently, I don't want to discuss anymore because there's no time for this. So we go to the structure of the dodecahedron. We have the PLC structure plastic of the generator polyhedron, and we go on to the structure of the skeleton of the generator polyhedron, which is actually covered with glasses to look into it. Now, the regular icosahedron skeleton parallelogram is based on the golden number 1.618, whereas the dodecahedron on the square of the golden number 2.616. The non-regular icosahedron is based on the square root of the golden number, which is 1.272. Now we have 1, 2, 3, we have the parallelogram of the dodecahedron, the parallelogram of the icosahedron, and the parallelogram of the non-regular icosahedron, interrelated. Now this theory goes on back about 35 years or so. According to Plato's philosophy, proposed solution for the world, the blocks building the polyhedra from lines where Plato's elements, where solids are different, Plato's elements, and then we go to triangular formations, areas, building further in 3 dimensions solids, and we go on and we build the pyramid model through this process, and we go on building this blue for the icosahedron parallelogram. These are also similar, and we go to also relationships with Nautilus and spirals via this triangle I referred to. Interrelated solid spirals, logarithms, science and art conference in Gazi of the Hellenic Physics Association 2008 presentation. This is the pentagon that I refer to, and we have the 54 degree, 1 over sine 54 degree related to this number 1.236 we find in the generator polyhedron. Now these are the unified solids. We put one together on top of the other, the icosahedron, the octahedron, and the trihedron. The tetrahedron is related to the cube. Here in this form, we see the tetrahedron incubated. So we get relationships all, and we have a space empty here. A dihedral angle, which is found in a section of dodecahedron. This is the dodecahedron, and we find this angle in the dodecahedron. Now this is the same, yes, and these are the numbers, and epsilon is 41.81 is the angle that we relate to with dodecahedron. Tetrahedron within cube relationship, I show to you this figure. Now, structure of the generator polyhedron, 4 times the theory scale with incubated dimensions approximately 16 times 16 centimeters. This is it. Now, so this is the cardboard skeleton of this polyhedron. Now, this skeleton is designed by planes with corners A, B, C, D, E, F, G, H, I, J, K, L. And we join, here's a list that we join these together in order to form the polyhedron. These are the coordinates of X, Y, Z coordinates, A, B, C, D.
Mr. Stefanidis, you still have 2 minutes.
2 minutes, okay, I'm going on, Professor. I'm going on to finish it. This is the section of the polyhedron. These are stereometric calculations. The work generator polyhedron gained a finalist highly commended award in London at the Institution of Engineering and Technology Awards in the section of communications, navigation and surveillance communications. They proceed on, this is it, the festivity. nominated as finalists by Boeing. This is a demonstration and presentation at the first Congress of Greek Mathematicians at the University. These are handmade structures. These are PLC. This is the work on computerized. And the conclusions, the presentation hopefully assists positively towards the sensitization for understanding of the conference participants and any other form of audience, so that it is clear as far as possible the theory behind the proposed geometry of the generator polyhedron via an application in optical satellite tracking. The results of structuring this model by independent parties prove the potency of this theory on which this polyhedron based, as far as its application towards a manufactured and put in orbit form of a special optical tracking satellite is concerned, it is left to those specialized in space technology applications. I thank you very much, Professor, and all the audience.
Thank you very much, Mr. Stefanidis. Now, if you can switch off the screen share.
Yes, yes.
Do you have, okay, now, we have for the next 30 minutes the Q&A session. We have some questions for you. Let me start immediately.
Yes.
The first one.
Yes.
If you can switch off your microphone, Mr. Stefanidis.
Switch off the microphone, sorry.
The first question is from Professor Michael Skoulos, and it comes from Mr. Charokopoulos. The question says, could the term nexus in sustainable development be translated by the universities in new educational and training programs, creating in this way a new kind of cross-cutting synergies among different scientific fields, and promoting the internationalization and reorientation of the current trends in higher education? This is from Professor Skoulos. Professor Skoulos?
Yes. I didn't capture 100% of the question of Mr. Charokopoulos. The first part of the question is about the WES, the WEFE, the water, energy, food ecosystem. Again, as I have done with tetrahedron, you have to imagine a tetrahedron with all these four, water, energy, food, and ecosystem. The proper definition of the right mix of this is site-specific and society-specific. What I mean is that in an area where you have hydropower, for example, the most important parameter is how to enhance the efficiency of water use after, let's say, the generation of energy. It is a different thing when you have to pump water from a ground aquifer using conventional fuels. It is always, what is important here is that you don't have technical solutions or political choices that neglect the other sectors, the other policies, because it is a continuum. This is the main idea. So what we can teach, your second part of the question, is the necessity to understand, and I said that before in my intervention, the interdisciplinarity. What is absolutely necessary is to respect the scientific knowledge and background of the other sectors and integrate the different knowledge. And this integration, we've heard about by many speakers, is one of the most fundamental parts that we have to teach, because this is rather new. I mean, even in our department a few years ago, Andonis knows very well, it was so difficult to convince people that we have to move, let's say, ahead of specific sectors, even within chemistry. I have to say that we have 7 eyes in doing that, in integrating, which is the information, and this is important because integration leads to implementation. Integration is a tool for implementation, but in order to get into that, you need to have the information. You have to build on innovation that it was raised throughout the meeting. And these two have to base also on involvement of scientists and the society, and also international. We don't reinvent the wheel. So international cooperation in bringing in all these things. So to conclude, the WIFE safety, the water, energy, food ecosystem, is an integration in application, is applied integration. And in order to achieve that, you need to prepare your learners from different disciplines through what I mentioned before, to at least know what they could expect from their colleagues in the other sectors. And this is a very simple answer. I need more time to explain in detail, but I think this is something that may actually encapsulate the idea behind.
Harry, I know that you have to go to your lectures, but yeah. I have one question, more philosophical. Especially after the speech by Professor Vermont from Yale University, the same question comes to me very often. Do we respect the environment, or we respect the money we get by destroying the environment?
I think it's a rhetoric question, because the answer is obvious. We cannot survive with money. We have to have the natural capital, which is the only capital we have. We do know as scientists, this is the only capital we have. And the market is also based on that. What we need to understand is that there is a dynamic relationship between the natural capital and all other capitals, and markets have to obey that. This is why today all the economists actually admit that we cannot have an economy that does not respect the natural basis, the environment. So it is, we have to understand two things. The investment in protecting the environment is an investment, and in the mind of all people, there should be, we should follow the proportionality principle. So what we invest should, in the mind of everybody, have a return. This return is not so visible by everybody, because we have the nature based solutions, pollination, absorption of the risks because of the floods, the droughts, and all these kind of things, which has a cost. Otherwise, there are billions of damages, and we pay that or through insurances or direct subventions from the countries to the population. So, in fact, at the end of the day, and the second part, of course, is the apart from the major intrinsic value on which I put more emphasis, there are a number of economic returns. So at the end of the day, there is no such a dichotomy, environment or development or economic return, because these two, and you know very well, Andoni, that was one of my first lectures in the University of Athens when I was still, a student. So economy, ecology, confrontation, and reconciliation. It goes back to 74. So we have now all the economists agreeing that there is no other way than integrating in the costs also the maintenance of the ability of the ecosystems to provide their nature-based solutions. So I think this has to be clear to the mind of all people, leaders, economic leaders, and investors. There is no other way. There is no other way.
Thank you, Mikhail. I don't know if Professor Vermont would like to make a short comment on that. The microphone, please. The microphone. Okay.
Sorry, I agree completely. I think that our challenges in this space are immense, and the need for urgent and rapid action at the global level is urgent. As you know, in less than 2 weeks, we have a major election in the United States. And some of us would like to see new leadership that takes climate change and the threat to humans more seriously. We would like to see rejoining of the Paris Climate Agreement. We'd like to see restoration of the regulations in the US for clean water, clean air, reduction of fossil fuels. You know, if I'm not mistaken, the US is still the largest economy in the world, a little bit bigger than China. And for us to be so wasteful in the US and for us to contribute disproportionately to the crisis of global warming, not to be part of the solution, but to be part of the problem, is a great tragedy and something that we are striving mightily to fix. Why in Europe there's a greater consciousness as to the importance of global warming and climate change and less consciousness in the US, I just don't know. It's one of these great mysteries as to why public discourse in the US has become so anti-science. I think that's one thing we can all agree on, that all of us scientists have to become better at communicating complex scientific issues to lay audiences and to policymakers. I don't think we are as good at communicating to the general public as we are to each other. It's much easier to submit a peer-reviewed publication rather than have a politician or a policymaker or a community leader understand what we're talking about. So in our school, we're redoubling efforts to educate all of our students and faculty in principles of public communication. And we think that may be part of the solution for the difficulties we're having in the United States, being part of the solution rather than part of the problem.
Thank you very much.
Mr. Chairman, may I say something I think relevant? one of the things we have done, and we have been instrumental in the University of Athens, is that we have passed from the Council of the Rectors of the Greek universities the charter, the sustainability charter for the Greek universities. We have been instrumental in preparing the draft together with colleagues from other universities. I think the Athens Calls Athens may circulate to other universities in other countries this text, perhaps as a source of inspiration, because it has been welcomed by by UNESCO and several other countries. So perhaps this is a right forum to share this charter.
I will make a comment, a short comment to Professor Edmund. Our countries expect much more from the United States of America. Now, I think we can give permission to Professor Skoudis to go to his lectures, and I will continue with the second question that goes to Professor Litke and Professor Amditi. The question says, as we live in an era characterized by the term hybridism, how the creation of smart cities influences the resilience of a smart city regarding the threats on cybersecurity on all levels, e.g. citizens, small communities, etc. Do you think about a comprehensive approach to that? Is it clear for Professor Litke and Professor Amditi? Professor Amditi is not here. Professor Litke is here.
Mm-hmm. Yes, very interesting question. It's true that, let's say, the widespread adoption of all of those Internet of Things technologies come inevitably with a risk and the associated threats that are, let's say, somehow are going to even more emerge during the next years. So from my experience, from what I see also as a common practice, is that nowadays, all those stakeholders who are involved with the design and implementation of Internet of Things infrastructures, they, let's say, pay special attention also on the different threats, the threat models that come with it. So there is security by design in this compared to, let's say, what was happening several years ago. But it's true that those new infrastructure, the hybridism, as very nicely put, will have to define also new ways and new approaches on how we position ourselves into this infrastructure. So it's true that the citizen should be even more aware of the different threats and cybersecurity now that might affect not only his PC, as it was the case 20 years ago, but rather also his everyday life, the context surrounding him, with all those sensors who might even intrude somehow in his daily life. So bottom line, it's true, it's a problem, but there are definitely means that can assist into providing not only more resilient Internet of Things infrastructures, but also more secure infrastructures.
Thank you very much. One question for Professor Mouzakis. This 3D printing is excellent. It seems that it can do everything. Nevertheless, can we do human organs with 3D printing, like lungs, heart, etc.? Professor Mouzakis?
Yes, Mr. Chairman. Thank you for the question. As myself, I am being also into bioengineering and biomaterials. We are not yet at the point of creating artificial organs, so to say. The best efforts for up to this moment are to create scaffolds mimicking some types of human tissue, like ears, like nasal bones, like parts of our bones, by 3D printing by several techniques. There has also been an effort to create a bronchial tree that saved the life of an infant which was born without the basic structure of not the lungs, but you know, the bronchos tree to produce aspiration. So yes, for the time being, it looks that in the near future we will be able to reproduce human organs. How soon, I cannot predict. There are some, let's say, complicated issues there. We have, for example, organs with multiple functions, like our liver and our spleen, and it's not so easy. But there are very, very strong scientific efforts to go there.
Thank you very much. Now, there is a question for Professor Mouzakis and Professor Melagraki. The question says, how we could institutionalize holistically within the industry and universities and research centers for collaboration among ChemInfo 3D printers, components, quality, and subsequently the quality of the outputs, which then will be used in much cities. Professor Mouzakis or Professor Melagraki, if the question was clear.
Let's say yes, it's a little bit on a gray area. I will take my part in terms of the materials manufacturing and systems manufacturing. If we have smart materials which we already know their behavior, electrical, magnetic, electromagnetic, mechanical, chemical, chemophysical, all these aspects. So if by simulation we have created materials which we know their behavior, of course, we can go to the next generation of 3D printing, which is called 4D printing. And it's about printing smart materials. So the answer is yes, it's feasible, but we need scientists like Dr. Melagraki, which will provide us with the characteristics of the materials or even the structures for new materials, which chemists like you, Professor Kalokerinos, will synthesize.
Okay, Professor Melagraki, does you want to add something?
Yes, just to add a few lines, I see a lot of synergies there. I see that for sure cheminformatics could significantly first help in the design of the experiments, for example, in order to select the best set of parameters. And then I see that we could, via the virtual screening procedure, we could lead to a rationalized decision based on which experiments to prioritize. And so I see that there is a lot of space for collaborative action, which I think it's very important for chemoinformatics going hand by hand with material science and 3D printing.
Okay, thank you very much. Now, we have some more questions, but time is running very fast. I think we should make a break for some lunch, some of you. And I think that we should all come for session number 2 at 2 o'clock sharp, provided that Professor Chekeris agrees. I don't know if he's with us.
I do agree, Professor, okay.
Now, I would like to thank you all for being in the first session of this conference. I understood that technology is running very fast, probably faster than we can understand. Unfortunately, we don't have time for all the questions. Therefore, I would like to thank you. I would like to call you back at 2 o'clock sharp for session number 2. Thank you very much for being with us this morning.
Thank you. Bye-bye.
Thank you. Bye.
Thank you very much. Bye-bye.